Good morning, good afternoon, or good evening, depending on where you are in the world. My name is Julia Godinez, and welcome to today's DevOps.com webinar, How to Fail Fast with Test Intelligence in CI, brought to you by Harness. We have a great webinar for you today, but before we get started, I need to go through some housekeeping announcements. Today's event is being recorded, so if you miss any part of the webinar, you will be able to access the recording for on-demand viewing. We will be sending out a link to access the webinar on demand, or you can visit devops.com/webinars. We want to hear from you, so please feel free to send in your questions at any time throughout the program by using the Q&A tab. We also encourage discussion by using the chat tab, so let us know your thoughts or just say a quick hello. The slides for this presentation have been made available for you to download. Just head on over to the handouts section and click download. Finally, stick around until the end because we are doing a drawing for 4 $25 Amazon gift cards, so stay tuned to see if you're a winner. Joining me today is Shiv Ningappa, Principal Software Engineer, Harness. And with that, I'm going to put myself on mute, turn off my camera, and let you begin.
Thank you, Julio. Hello, everyone, and thank you for joining me today. I'm really excited to be with you all to talk about our test intelligence journey in CI here at Harness. First, a little bit about myself. My name is Shiva Kumar. I am working as a principal software engineer at Harness. First, I joined more than 1.5 years, and I've been working as an architect for our continuous integration product ever since I joined. And before Harness, I worked at Uber ATG, where I built a simulation infrastructure to test self-driving car software. And prior to that, at Yahoo, I built many complex, low-latency data processing systems that ran at a scale of billions of events per day. Now, we all know that software is eating the world. There are 60 million software developers in the world as of now, and this number is expected to grow to 100 million by 2025. We are writing so much software every day. However, the software development process is not getting faster or easier. So here at Harness, we're looking, okay, what is that stopping? What is the bottleneck in this whole software development lifecycle? How can we improve it? How can we move fast? So there was a recent survey conducted by GitLab and NewStack to understand, okay, what are the bottlenecks in software development lifecycle? And as we all can guess, testing is the biggest bottleneck. And this is the same sentiment we have noticed here at Harness also, and along with our customers. On the left side, as you can see, this is the survey results by GitLab, and majority of them said yes, testing is the biggest bottleneck. And then at the right side, these are the results from a new stack, where the same sentiment was echoed, that majority of the responders said software testing is the biggest bottleneck. So we are writing so much software and we want to move fast. We want to bring our product quicker to the market. So what happens if we are not, we are compromising and we are not testing thoroughly before we push it to the market? Well, we all know that the innovation is at risk without quality. There have been many examples where the without quality caused so much disruption, and we cannot move with innovation without quality. And so quality and innovation have to go hand in hand. So we made some observations lately. First one is lengthy unit testing cycles. So as we are writing more and more software, we are also writing more and more unit tests to test this software. And now we are trying to get as much coverage as possible, reaching 80%, 90% code coverage, wherein 90% of the software we write is being tested by unit test, right? So as we add more code, more unit test, the testing cycle becomes lengthier. Here at Harness, we used to have we have a monorepo which hosts most of our backend source code. Used to have 10,000 unit tests last year, and now we are close to 18,000 unit tests. So to run all these unit tests currently takes 300 minutes without any caching. So we have split it into 5 parallel jobs, but still the testing cycle is lengthy. And the second observation is the time for the first failure is very, very slow. It can, without cache, it can take about 45 minutes, at least 45 minutes to know if there is any failure in the unit test. And then now, gone are the days where we were making changes to hundreds of files at once and then raising one big pull request or merge request or diff. Right now, we are making incremental changes. And so every incremental changes, we have to run all these unit tests again. Here at Harness, we have about 300 engineers. So each time an engineer makes a small change, we have to run all these unit tests, which results in high infrastructure cost, as we all know, due to repeated and mostly unwanted tests. So how do we tackle these problems? Well, we have embraced the fail fast methodology. Okay, what are the benefits of this fail fast methodology? First of all, as an engineer, you want to get like quick signal to fix the issue. As soon as I kick off the build, I will get a signal faster rather than waiting an hour to know some issue. I'll get the signal quickly. And there will be no waiting for the lengthy build process. Suppose I raise a PR pull request and it takes 45 minutes, then what we usually do is like we context switch and work on some other task. And if there's any failure, and again, like we context switch, come back and try to fix this failed issue, and so on. And we all know context switching is expensive. So the benefit here is, yeah, I don't have to context switch. I get the signal quickly. So there's no waiting for the lengthy build process. And now there's a fundamental shift in engineers to move fast. So if it's taking like a 45 minutes or 1 hour for something to test, then the tendency is, okay, make sure it is all fine, it is all like working locally on the machine, and then go raise a pull request, because it is too lengthy to get to know if there's any failure. So this slows down the development uh, velocity. So suppose if I get this signal quickly, what I do is instead, like I would, rather than like testing everything and then making sure there's no error, I'll just quickly raise a PR because I'll get the signal faster. So this changes in the mindset of moving fast. Okay, these are all good, great. So how do we build it? How do we embrace this fail fast methodology? Well, the answer is test intelligence. So the test intelligence is, it actually accelerates the entire dev cycle without compromising the quality. So that is the key aspect. And then it increases visibility into the test cycles. It provides all the important insights into test results and the failure, error message, and everything. And also, it helps to identify the gap in the code coverage. So if we look at the testing funnel, at the top is where the source code resides. And then we at the top of the funnel, and then we run like a static analysis usually, and then linting and so on, which catches the obvious bugs and errors. But then the next is the unit testing. So this is where majority of the code is tested. I mentioned like the trend is 80-90% code coverage. So every piece of software we write is tested thoroughly in this layer. And then the functional test, UT testing, and so on. So we need to catch these bugs as early as possible in the process. And currently, we have added test intelligence at the top of the funnel here at the unit testing. Now, okay, what is that? The test intelligence, the whole philosophy of this test intelligence here is run only the important tests. Okay, what is the meaning of important test? The meaning of important test here is it so that it confirms the quality of the code change that triggered the build. In this example here, you see there are 8 tests, and out of these 8 tests, let's say there's a pull request came in, and I don't have to run all the 8 tests. So instead, based on like what changes came in, the test intelligence selects, okay, only T2, T5, and T7 are good enough to test this PR without compromising the quality. So as a result here, instead of running 8 tests, we run only these 3 tests. This is the core principle of the test intelligence. At a high level, how does this whole thing look? And then I'll go into deeper details how we actually build it. So at a high level here, as you can see, there's a test runner agent, this box, which is running on the customer build form. So this agent is the one which has access to the source code. So when we are like testing a software, it knows the agent, the test runner agent knows, okay, what are the changes happened? What are the modifications happened in this particular pull request or merge request or diff? And then it sends that list to the test intelligence service, which is running on the harness infrastructure. Now, this test intelligence service, it has all the knowledge about all the source, test, and resource data. So based on the change set it received from the agent, the test intelligence service selects the subset of the test and then it sends the subset list back to the test runner agent. And this test runner agent eventually runs only those small subset on the test step container. And notice that here the test runner agent is making use of underlying build tool, like in Java, it could be Maven, Bazel, or Gradle. Once these tests are run, the test runner agent, it parses those test results, and then it sends 2 pieces of information back to the test intelligence service, which is the test results itself, and then the partial call graph that is generated as part of running these tests. And finally, test intelligence service, it receives the partial call graph. And now this particular PR might or might not be merged to the master because some PRs get abandoned for whatever reason. However, so we cannot prematurely go update this partial call graph with our master copy of the call graph. Now, whenever we get a notification from Git, okay, this particular PR is merged, that's when the test intelligence service goes and updates the partial call graph with the master copy. And that's how the call graph is in sync with the source code. Okay, now the next question is, okay, this is great. How does the test intelligence service know how to select this subset of tests? So that's where the instrumentation comes into picture. Currently, we are supporting Java, .NET, Python, and Golang are being added. So in the Java specifically, Maven, Gradle, and Bazel are supported build tools. What we do here is at the beginning, as part of the bootstrap, we first like raise a pull request. Now, since we don't know, the test intelligence service doesn't know anything about the repo, so it just says, okay, run all the tests. Example, in our portal monorepo, harness portal monorepo, we have 18,000 unit tests. We run all the bootstrap process, we run all the 18,000 unit tests. While running these unit tests, there is a Java agent which we attach on the fly to the bytecode. So this agent, what it does is it records all the method entry exit to create the call graph. And we also record various annotations, for example, at test. And that's how we identify whether a method is a test or source. And in addition to that, we also intercept all the resource files read to identify whether a file is a resource, and we map it to the corresponding test. So with all this information, we know what is the relation between test, source, and resource files. And so when a specific test is when specific source code is modified, we know like which test to run. Right. So once there's we generate this call graph, we run these 18,000 unit tests, and when the JVM shuts down, the entire this call graph what we just built by recording all this memory exit, that is returned to the file system here at the desktop container when the JVM is shut down. And the test runner agent, it takes this data of the call graph, and then it encodes into arrow format and sends it back to the test intelligence service. And the test intelligence service takes this data and stores in the data store, the entire call graph, and which will be eventually used by the selection algorithm. So this is like the entire mechanism of how we build the relationship among source, test, and resources. Now, if you visualize like this whole thing, there is like a source. This is how it looks. There's a source, test, and resources. They are represented as nodes, as you can see here. Here, the purple pentagon is a test, and the circle is, it could be a resource or it could be a method. In this specific example, there's a blue circle. Those are modified in this specific PR. And they are directly or indirectly called by this pentagon, which is a test. And that's why for these changes, these 8 source changes, we chose this pentagon, this specific test. Now here, an edge represents the caller-callee relationship. And then it also gives a clear indication of confidence into why a specific test was selected. Now, with this knowledge, let's look at a demo and see this whole thing in action. So what you're seeing currently is a sample. This is the actual file in our portal backend monorepo. Let's say I make a change here. I'm updating this specific file, ta build tool.java, and then I raise a pull request. Get a pull request. And as you can see, this is the file I changed, ta build tool. It would take some time for this for the build to complete. So I'm showing you a build which already completed for the exact same change. As you can see here, let's look at this is the PR which actually triggered this whole build. And here, this is exact same change. I updated this TI build tool. And as you can see, there are total close to 18,000 unit tests. Now the test intelligence decided to select only 2 tests because there's no need to run all the tests because of the changes. And as you can visualize here, this is the change I made, TI build tool, which comes from the package here. And this the type is source. There's a unique ID for each node. And then, as you can see, this is the test, which is actually directly or indirectly calling this a particular source, and that's why this was selected. So we know this information because these tests were run earlier, and we have built this entire call graph. But like in a PR, there's a case where we might add new test case or update a test case. Then the selection algorithm will simply go and include those tests as part of the subset test. So you see this now, I get signal in like 5 minutes, thereby saving like 56 minutes, right? And whatever the files the test we selected, we break it down into multiple buckets. One is or like a true or correlated with code changes, and uh, nothing is correlated with new test or updated test. And if we look at the pipeline itself, this is how it looks, wherein first, like in the git clone, we check out the code, and then we do some setup. And this is where we actually run this entire test intelligence unit test. Right? So how would somebody use this? It's very easy to use in the sense, as I mentioned, most of the cases there's no change that I need to make to my source code or like a test. All I have to do is just like use this to show you this step, wherein this is like how we configure, like provide the some name for this step, and then the image where we need to run this unit test. What's the language we need to run, and what is the, like the build tool and any arguments. And this is we don't have to provide this. This is the prefix of the packages that I need to instrument. So there's two ways to actually generate this call graph. One is using like a include list, or another one is exclude list. So if we go with exclude the package prefix, then it is not like a performant. So instead, like we go like scan all the source code and get the list of all the prefix packages and instrument only those packages. That is for the performance reason. And that's it. Just create this step, and everything else is done by the test intelligence service. So with that, actually, like for that same PR, two tests, one test came in one of the jobs here. This is like one of the pipeline which ran one test, and this is another one which ran out of those two selected, because as I mentioned, we have split our unit test into 5 parallel pipelines. So as you can see here, yes, that particular PR failed for a reason here, and I get the signal immediately in like 4 minutes instead of waiting for close to an hour, right? Yeah, that's about the demo. Let me go back to slides. Yeah. So while building this, we encountered many challenges, and I would like to highlight one of them here. There are some tests that process classes as symbols, but not as code. This is typically the case if a class is processed by annotations via reflection, but where no methods or constructors are invoked. As an example, take this following snippet here. So this test asserts that all subclasses of a given interface, my interface, are implemented under a given package, com.acme, right? So here there is no invocation of any methods of my interface. So the JVM does not offer a standard method of discovering this test dependency on the state of my interface's subclasses, such as their package location. And while it would be in theory, it's possible to discover this dependency automatically. However, the processing power that this discovery would require would be uneconomical. So therefore, now we require that methods that produce classes as symbols, which find relevant classes, would be added to test class names calgraph if the annotation was added to the former method. So as a consequence, the test class names method would be rerun if a superclass of my interface was added, only if the annotation was present. So this is like only like a some special case where we need to add like one annotation, for example, at hardness trace into such test. And that's other than that, there was no change in the source code or the our test methods or any other configuration. Now, yes, this is all great. Like, what is the impact? Like, what are the results? Is it helping in any way? Let's take a look at the real-time graph we have to measure this success. So first, like we added the test intelligence back in July. So the blue line, what you're seeing here is the average time it takes to run the unit test on a daily basis. This is like without intelligence, the blue line, whereas the green line is the same metric with intelligence. So as you can see, we were about 45 minutes or so, and then gradually, and now with test intelligence, we are able to run this entire unit test under 20 minutes. And then, so also in the selection algorithm, we have taken a very conservative approach in the sense, suppose when the pull request comes in and it has some changes to files, for example, pom.xml or build.bazel or workspace, some configuration which we don't understand, right? In which case we fall back and just run all the unit tests and we call it full run. So excluding those full run, what is the percentage of tests we have been selecting in our hardness portal, the backend monorepo? As you can see, consistently we have been selecting about 2%. There's some like issues here over the weekend here. Excluding that, we have been constantly selecting about 2% of tests. But then, okay, that's good. Let's say we put everything together, including full runs also, then what is the percentage of tests we are selecting? That here, as you can see, on a daily basis, anywhere between 40 to 60% of the tests are being run. So instead of running 100 all the time, all the tests, we are running about 40 to 60%. And this is causing a direct impact on the cost also. Right? And then, okay. So then these are the numbers. A portal is our backend monorepo. Without intelligence used to be 38 minutes, and with intelligence 18 minutes. As you can see, it's about 52% time saving for all the engineers. And in addition to that, we also wanted to test this on some open source projects. So the methodology was uh, we uh, took some open source Java open source projects, and we went and replayed the commits, the actual commits that happened on the open source repo for the last 2 months, or and then collected what is the time save. As you can see, depending on the project, it varies. It varied from anywhere from 20 to like a 65% time saving. So this exercise was done a little bit earlier, where we didn't have uh, the support for resource mapping. So now we have a support for this resource wise mapping also. I'm sure it would be better than these numbers if we do the exercise again. Then we have, if you are interested to know more about test intelligence, we have a cool blog written on our Harness website. Please scan this QR code and head out there to get more information. Having said that, I am open for Q&A.
Yes, we do have a few questions here, and just as a reminder, if you'd like to post a question, just head on over to the Q&A tab and to submit your question. First question we have, in the past, test cases are developed prior to coding. With agile development, test cases are developed per sprint. Sometimes developers will even wait until coding is completed. Will test cases be defined prior to coding better?
Okay. Yes, this is a good question. This is what you're saying is tester-driven development, TDD. So actually, the TDD helps when actually the developer is actually writing the unit test. So in the sense, it solidifies the requirement before actually writing the code. So I have practiced this TDD earlier, and I really initially I had some hesitation whether because usually as an engineer we want to like write some code quickly and then try it out how it works, right? But with the TDD, there's a shift in the mindset. Okay, first write the unit test. Yes, they are expected to fail because there's no source code exists. So you write the unit test, they fail, and then you go write the actual code, and then they keep passing. Yes, it's a very powerful technique, and personally, I highly encourage that technique, TDD. Yes.
Great. Next question. How easy is it to implement test intelligence?
How easy is it to implement test intelligence? So, uh, I need some clarification. Is it like how easy to use our test intelligence, or um, I assume like, is it like how easy to use our test intelligence, what we have built?
It wasn't incredibly specific, so
Okay. Um, okay, I'll talk to with in reference to harness test intelligence. It is as I showed in the demo, it is very easy to use our test intelligence. There is no change in the source code, test methods, or configuration. All we have to do is create that step, um, and that's it. We generate the call graph, and we do the selection, everything on the fly. Yeah, so it is very, very easy. But except like one special case where I explain like we need to add a annotation, harness test annotation. Other than that, for the entire Java, it's super easy to use it.
Excellent. Next question. Can I implement test intelligence to any CI tool?
To any CI tool. So, okay, so the question is, can I use the harness test intelligence to any CI provider, Jenkins, and so on? Well, that is the whole idea. What we have built is it is designed to work as like a separate product that it can be applied to any CI tool. That currently we are offering it as part of only the harness CIE. But yes, we have a plan to make it available to any CI tool.
Okay, and the last question I see here, what is the timeline for test intelligence? Will it just support unit tests?
Yes, so currently it supports only unit tests. And as we saw in the test funnel, we want to add support for the functional test. And that work is in progress. And I don't have a specific timeline when it will be available for functional testing.
Understood. And I don't see any other questions. We have plenty of time if you have any. So, in the meantime, I'll just want to remind everybody that today's webinar has been recorded. So, if you missed any or all of the webinar, you'll be able to watch it again. We will be sending out an email with a link to access the webinar on demand, and you can also find it on devops.com. Just look in the on demand section in the webinars page, and it should be there. Still not seeing any questions. I'll also go ahead and announce the four Amazon gift card winners that I had mentioned. Our first winner is Raphael A. Congratulations. Our second winner is Dave B. Our third winner is Felix S. And our final winner is Danielle G. So congratulations to all our winners. We'll be reaching out to you via email with instructions for claiming your Amazon gift card. So please check your inbox. And if you don't see it there, check your spam folder. Okay, so last call on Q&A here. Going once. Going twice. Excellent. Well, you really must have covered everything, Shiv. Thank you very much for taking the time to put this presentation together, as well as the demo. That was very informative. We really all appreciate it.
Thank you, Julio, for having me. Thank you, everyone, for attending this.
Of course, yes. Yes, sorry to interrupt. I'd also like to thank the audience for their time and engagement. This is Julio Godinez signing off until next time. Take care, everyone.